All right, so today we're gonna go over basically questions about Coulomb's law and electric fields. So last time we talked about what electric field, the focus was what it looks like, the patterns that it produces, what it is. So today we're gonna do some calculations with this. Okay, so we're gonna start with Coulomb's law, which is, if you remember last year, 1 coulomb is the amount of charge carried by 6 million electrons. So 6 times 10 to the 18 electrons or protons. That's each one carries a fundamental charge, which is actually what you're trying to determine in your milk and oil drop experiment. But I think I may have mentioned you could just very easily look up the fundamental charge of a proton or an electron, and it's this value here, okay, 1.6 times 10 to the negative 19 coulombs, right? So uh, Coulomb's law is a way to measure the force between two charged particles, given two things, given their charges and given the distance between them. Here's the equation right over here. So there is a constant, K, which I think I mentioned last time, which is 9 times 10 to the 9 newtons, uh, meters squared per, oh, sorry, where was I? Per coulomb squared, right? This is the constant. And I think the last time we compared it to big G, which if you remember, big G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So you can see that K is a much bigger value than G, because the electric force, or just electromagnetism in general, is just a much stronger force than gravitational force. So let's start with a really simple question. We're going to try to figure out the electric force between two charged objects. Now, I'm going to assume that these are the same charge because they're two balloons. So they are going to have the same charge. If you remember from grade, I think you do it in grade 9, you talk about static electricity, certain materials pick up charge, certain materials give up charge. So if they're two identical materials, balloons, I'm assuming they're made of the same material, they're most likely going to be the same charge. So we're going to assume that this is the same charge. So that could mean that they're both positive or they're both negative. So in this case, the force is going to be a repulsive force. Otherwise, if they were opposite charges, it would be an attractive force. But it doesn't say, it just says measure the force. So let's do this. So the electric force is a function of K times charge 1 times charge 2 over R squared. So K is 9 times 10 to the 9. All right, Newton meter squared per coulomb squared times Q1 times Q2. Now, they're both the same charge, so we could just say Q squared. So we could say 1 microcoulomb is 10 to the negative 6C, and we could just square that because it's the same charge, over R. R is 5 meters, so make sure the distance is in meters, squared. Okay, so if we do that, we get an answer of about 0.00036 coulombs. Sorry, newtons. Not coulombs, what's wrong with me? Or 3.6 times 10 to the negative 4 newtons. Okay? Questions about that? I mean, it's got the same form as the equation we did for gravity. You know, if you remember, the universal law of gravitation was big G m1 m2 over r squared. You could see it's a very, very similar form for the electric force. Okay? Any questions in regards to the first question? Okay, let's move on then. The next question is looking at an object, a positively charged object, a proton that is positioned adjacent to two other objects. So let's draw this out. So let's say that we have a proton that's over here. It says it's to the right of a positively charged object and a negatively charged object. Okay, it is 10 centimeters from the positively charged object. So that's a distance of 0.1 meters. Whereas the other distance, so from here to here, is a distance of 0.3 meters. Okay, so we're going to figure out the net force acting on the proton. Now, in this case, the two charges that are adjacent to the proton are opposite charges. So let's look at them separately. So we could say, let's look at the force between the proton and the positively charged object. So we're going to call that one, we'll just call it A, okay? So we're going to look at this scenario, the proton and an A, okay? Which is positively charged. Okay, so the force in that case is same equation as last time, KQ1 Q2 over R squared. So 9 times 10 to the 9. I'll leave the units out just to save a bit of space. Q1 is let's say Q1 is the proton. So proton carries a fundamental charge of 1.6 times 10 to the negative 19 C. All right. Times the charge of A. And it says A is 1 microcoulomb. So that's 10 to the negative 6. Over R squared. It's a distance of 10 centimeters or 0.1 meters. Okay, so if we work that out, that comes out to a force of about 1.44 times 10 to the minus 13 newtons. We're going to do the same thing between the proton, and we'll call the other object B. Let's use a different color. Let's use red. Okay, so we're going to the same equation. So there's no point in writing it out again. So we'll just say K times the charge of the proton times the charge of the other object. Now the other is 10 microcoulombs. So 10 microcoulombs would be 10 to the minus 5 over the distance squared. The distance is 30 centimeters or 0.3 meters squared. And that will give us a force of 1.6 times 10 to the negative 13 newtons. Now we have to consider the direction of these two different forces, okay? So object A is going to attract, so it's going to try to move the proton towards it. So we'll just say left is negative. So we're going to make this negative, all right? And object B is going to repel. I'm sorry, other way around. Other way around. I thought A was negatively charged. So other way around. Sorry. So object A is going to push. It's positively charged, not negatively charged. So object A is going to want to move the proton away. So we'll say right is positive then. Okay. Object B is going to want to move the proton towards it. So we'll make that one negative. Okay. So then the net force will simply be the sum of these two forces. So positive 1.44 times 10 to the negative 13. And negative 1.6 times 10 to the negative 13. That's going to add up to 0.16 times 10 to the minus 13. Negative, which means that it's being pulled to the left. Okay. Or 1.6 times 10 to the negative 13. Negative 14 newtons to the left. Okay. Any questions about Coulomb's law and electric force so far? We're all good?
Sir, I have a question.
Yeah.
How do we like convert from a microcoulomb to a coulomb, or like how does that work?
Okay, so yeah, I shouldn't assume that everyone knows this. So it's no different than when you did measurements. Like for example, if I said to you, what's a centimeter? A centimeter is 10 to the negative 2 meters, right? So centi means 10 to the negative 2. Milli, a millimeter, milligram. I guess a millicoulomb would be 10 to the minus 3. This is 1,000th, right? Micro is 10 to the negative 6. So that's a millionth. So a micrometer would be a millionth of a meter. So that's 10 to the negative 6. Now, if it's so 1 microcoulomb would be 10 to the negative 6. 10 microcoulombs would be 10 to the negative 6 times 10, which would give you then 10 to the negative 5. Okay. Then there's nanocoulombs. Nano would be 10 to the negative 9. Actually, in the next example, we have something called a picocoulomb, which is 10 to the negative 12. So nano would be a billionth, and a pico would be a trillionth. Okay? You're typically going to come across micro, which is a 1 millionth, 10 to the negative 6, and nano. Those are the two most common ones that you'll see, which is 10 to the nano being a billionth or 10 to the negative 9. I just threw in the pico, but I don't think you hardly come across that one. Does that help?
Yeah, thanks, sir.
No problem. Okay, so let's look at number 5. So here we have an object that is has a 5 picocoulomb charge object, and it's basically keeping a proton stable in a vertical position relative to the ground. So let's imagine that here is my charged object. Okay, it's positively charged, and then there's some proton. So it's some distance up from my charged object. We're going to figure out how high does this thing need to be so that it's in a stable position, okay, above the ground. So if it's not going up or down, what does it tell us about the forces?
Equal?
Yeah, so there obviously is we know gravity is going to want to pull the proton down. So we have the two forces that must be balanced, right? The force of gravity and the electric force have to be balanced out. Now, a force of gravity, we know what that is. We know that's m times g, all right? And then we know now what the electric force is. Electric force is k q1 q2 over r squared. So in this case here, we're trying to find its position. So we're going to look for r squared. So we're just going to rearrange. Okay, and then we're just going to solve for r. Okay, so r is going to be the square root of k, 9 times 10 to the 9, times q1. So q1 is 5 picocoulombs. Times the charge of the proton, which we recall, is 1.6 times 10 to the negative 19 over the mass of the proton, which is about 1.7 times 10 to the minus 27 times g. Now, in this case, g is fine because the distance you'll see is not that great. If the distance was like hundreds of kilometers, then obviously wouldn't be able to use g because g would be different. But in this case, you'll see the distance is not that much, so we could use g. All right, so if we solve for r using this equation, we get a distance of about 657 meters. So at this distance of 657 meters from the ground, or from this plate, sorry, I should say from the plate, assuming the plate is close to the ground, then the two forces would be balanced. Okay, any questions about that so far? Okay, so here's a question that I included. I don't think that there is an exam for this course anymore. I'm not 100% sure, but I'm pretty sure that there probably won't be an exam. So I have no problem showing you this because I have this question that was on an exam in previous years, and it always gave students a hard time. But the solution to this question is actually quite easy. This is example number 4. Okay. So imagine we have two charged particles that are separated by a certain distance. Now, this is a certain distance. So what does that mean? We have no idea what that means. Certain distance could be anything, right? And they each have a charge of 1 picocoulomb. So I'm using picocoulombs again. And the question is, what are their masses? And I remember giving this question, a similar question like this, and a lot of kids would just scratch their heads. Like, what do you do? We're missing so much information here, right? But the thing is, sometimes if the information is missing, there's 2 reasons. A, I forgot to give you something. And given how many times I've done that in the past, there's a good chance I probably forgot to give you something. But in this case, it's B. It's because it's not important. All right. And let's take a look at why it's not important. Because if these two, oh, I forgot to mention one thing in this question. They are in a stable position. I have to mention that. Otherwise, you can't do this question. So they are in equilibrium. So they are not moving, in other words. So they are not moving. That's really important. You need to know that. Otherwise, you can't do this question. So they're not moving. So it's kind of like the question before, which means that the forces are balanced. Okay, so that means, again, Fe equals Fg. But we can't use mg in this case. We're going to use the universal law of gravitation. So if they're not moving, these two forces are equal. We know the equation for each one, right? We know Fe is K Q1 Q2 over R squared. And Fg is big G M1 M2 over R squared. You'll notice the actual distance is irrelevant. It's the same on both sides. So the distances actually cancel out. Now, it says that the objects are identical. So their masses are identical and their charges are identical. So we can actually make this a little bit simpler and just say that means kq squared, because q1, q2 are the same, would be equal to gm squared, because m1, m2 are the same. So now you can see that m would simply be kq squared over big G, right? Take the square root of that. So if I finish it off, m would be the square root of k times q squared. Picocoulomb is 10 to the negative 12 squared over the gravitational constant, which is 6.67 times 10 to the negative 11. Okay. All right. So if you do that, you get a mass of about 0.012 kilogram. All right. Any questions? No questions? Okay. So let's move on. So these questions are all in relation to Coulomb's law. So now what we're going to do is we're going to just take a look at the relationship between that and electric field. So first time we talked about what an electric field is and visualizing the electric field, looking at the patterns that it produces. If you recall, we talked about, like a positively charged particle generates a field that radiates outwards, and a negatively charged particle radiates an inwards field. What we're going to do today is we're going to talk about the strength of this field. So the electric field is defined as basically the amount of force per charge that a point charge generates. So the unit is going to be newtons per coulomb, all right, because it's force per unit of charge. And from the previous calculation, force is K Q1 Q2 over R squared. So if it's force per charge, that means it would be, you can simplify this then, because the Q's would cancel out, to K times the source that's generating the electric field over R squared. This would give you then the electric field strength for any point charge, K Q over R squared, or just simply F over Q. So let's look at an example. So what would be the electric field strength for a 2 microcoulomb positively charged object at a distance of 2 meters? So let's say you have an object that would be 2 meters away. What kind of, assuming it's charged, what kind of force would it experience at that distance? So the electric force, I'm going to use little f to, as a little subscript, the E little f, electric force, electric field, sorry, is K Q source over R squared. So the constant we know is 9 times 10 to the 9. My object is 2 microcoulombs, so it will be 2 times 10 to the negative 6 over the distance squared. So the electric field strength for this object would be about 4,500 newtons per coulomb. That's it. And then if you have any charged particle in the electric field, so if this is a positively charged object that's radiating a field away at a distance of 2 meters, if we have an object that is positively charged object, as long as you know the charge, Q, then obviously Q times the electric field strength would give you the force that that charged particle would experience, right? So you can see there's a relationship between this and what we were doing previously. Okay, let's do one last example, and then we'll wrap it up. Okay, question number 6. Now, question number 6 is, I was looking at this, and when I did it initially, I was like, wow, this is a good reminder of just how there's a big disconnect between things like at the big scale, the macro scale, and the micro scale. We don't know if you ladies are familiar with the problem in physics, the trying to unite or unify the quantum world with the macro world. Do any of you know about this problem?
like they're trying to use the string theory and stuff.
Yeah, so that's an approach. So you want to enlighten us as to what, like, one major issue? Like, what's the issue here?
Between the micro world and the macro world?
Yeah.
Yeah, like the laws that apply to one don't necessarily apply to the other.
Yeah,
Okay.
there's some sort of a disconnect there, because you would think if they're laws, they should be applicable in all scenarios. But there's obviously this bit of a problem. So I'm going to show you like an example of this, and this is kind of a neat example, because the next unit, don't worry, we're not going to start the next unit right away because we haven't finished this unit. But the next unit is special relativity. So you're going to see in that unit that things get a little bit weird. All right. And things get really weird when you start approaching the speed of light. And in the unit after that, we talk about talk about quantum mechanics, and the world gets even weirder. All right. So when I was looking at this question, I just made up this question. I said, let's look at an example at the micro scale. See what happens when we look at really small distances. So I said, let's look at, for example, a hydrogen atom. So I looked up. Okay, let's look up what's the distance, the average distance between an electron and the nucleus. The one proton. What's the average distance between these two objects? And I think I actually have the distance incorrect, though. Let me just double check what the distance is before we do this question. Let me just double check this. Hold on. Oops. Let's take a look. Sorry. Okay. Distance, average distance. This is going to be average distance, all right, between electron, proton, or hydrogen atom, okay? So it's 0.5 times 10 to the negative 10. So that's not correct then. This should be 0.5 times 10 to the negative 11. So let's fix that. Okay, hold on. Jumped all the way down here for some reason. Okay, so this is actually, well, okay, stop. Okay, what's going on here? All right, so it's 5 times 10 to the minus 11. Okay, so that's it. I wrote the wrong exponent down. Okay, so the question is going to be, what is the field strength for the proton at a distance? What is the electric field strength of a proton? Well, this is the proton in the nucleus of a hydrogen atom. And what would that electric field strength be at a distance of 5 times 10 to the negative 11 meters, which would be the average distance that an electron in that hydrogen atom would be? Again, average distance, okay? So from the previous question, the electric field strength we said is, screen is like just going crazy here. E is K Q source over R squared. Okay, so K is 9 times 10 to the 9. The source is the proton. The hydrogen atom has 1 proton, so we know the elementary charge is 1 times 10 to the negative 19. Okay, and the distance is 5 times 10 to the negative 11 squared. Okay, so if we do that, we get an answer, but let me just double check. So I did put in the wrong value, so I want to make sure that this is the right answer then. Okay, so wow, what's going on? Do you see my screen just going crazy? All right, let's try something here. Let's start the share again. Let's see what the problem is. Okay, girls, can you see my screen again? ladies?
Yep.
Okay, stop. I don't know what was going on. Okay, so K is, oh, here we go again. I don't know if it's my mouse. I think it's my mouse. Aha, I think I made a discovery. No, it's not my mouse. I spoke too soon. All right. My screen is going crazy here. Not sure why. Oh boy. Okay, let's. Seems if I have too many, I don't know what's going on here. All right, I'm just gonna just do this on my calculator without using the one on my computer. If you girls want to just double check this with me, this should be this should work out to approximately this number. Can you verify that? Because I don't know what's going on with my computer. It's just like not the first time it's happened.
Yeah, I got the same thing, sir.
Got the same value?
Yeah.
Okay. All right. So then I put the correct. Okay. All right. So that's good. Now, so that's the electric field strength at that distance. Okay. That's a very tiny. That's a tiny distance, right? Now, question. The follow-up question is, what is the acceleration of the electron at this point? So then, we can easily work out the force, right? So we know that F equals ma. So the force would simply be the electric field times the charge, right? Because the electric field times the charge would be F. So we can do a little substitution. We can say the electric field times the charge of my electron divided by the mass of the electron would be the acceleration experienced by the electron. Okay, so what would that value be? Okay, so the electric field strength is, what is that? 576 billion newtons per coulomb. I don't know why I'm not putting exponents. I really should be putting in exponents. Let's put in exponents. What am I doing? All right. 5.76 times 10 to the, what is that? 11 newtons per coulomb times the charge of the electron, which is 1.6 times 10 to the negative 19 coulombs, over the mass of the electron, which is about 9.1 times 10 to the negative 31 kilograms. Now, I got a number. If you want to verify this, because I don't want to jump to the calculator because I don't know what's going on with my computer. I got a value of about 1 times 10 to the 23 meters per second squared. Can you kids verify that?
Yeah, I got the same thing.
Okay. Now let's think about this for a second. I mean, let's think about how ridiculous this acceleration would be. 1 times 10 to the 23 meters per second squared. Now, if you were just wouldn't think about it, like this thing would reach, we have two problems. One is it would reach the speed of light in the blink of a second. Like, you can probably work it out, but I mean, in the tiniest fractions of a second, it would reach the speed of light. And we know from the next unit, things can't go faster than the speed of light. There's a speed limit. Okay, that's one problem. The other problem is, there's such an incredible force acting on the electron. The acceleration is so incredible. Why doesn't it just crash into the nucleus? Why doesn't it do that? Given this value, given these ridiculous values, I mean, look at the electric field strength, look at the acceleration on the electron, but we know the electron does not crash into the nucleus. So there's obviously a disconnect between the way the laws work when we're talking at the macro scale compared to when we look at the micro scale, the level of the atom, which is this is really, really, really interesting and fascinating stuff. So obviously, this is the calculated value, but it's obviously not doing this because the electron would not crash into the nucleus unless it's a neutron star, right? Then it would, but that would require some amazing amounts of energy. Okay, ladies, that's it. There are more questions, but we'll deal with those on Thursday. Any questions?
I have a question about the test.
Yeah,